Here's some more about capacitors. Here's a capacitor, and the formula for capacitance is the charge over the voltage placed across the plates. The charges were placed on the capacitor plates by the battery. The question I have is, what is the total charge on a capacitor? Look at the picture and I think you'll see it's always going to be zero. If one plate becomes positive, the other plate becomes negative. But when people ask you how much charge is stored on that capacitor, they only mean the charge on one plate. So this charge now will generate an electric field between the plates. After a long while, the capacitor is filled and that drop in voltage across the capacitor equals the gain in voltage from the battery. But we can also see that the change in voltage is equal to the strength of the electric field times the distance. And that's the distance between the plates. Now, technically, there should be a negative sign there because when you move in the direction of the electric field, the voltage is a drop in voltage, not a gain in voltage. But right now, we don't need to worry about the negative sign. So what could you do to increase the value of the capacitance? If I got a bigger battery with more voltage, I would increase the voltage, but I'd also increase the charge getting placed on that capacitor. It would still leave me with the same constant, C. How about make the plates larger? The charges would be able to spread out. That would make more room for more charges to flow in. This would increase Q, but the voltage would stay the same because that's limited by the battery. Now let's disconnect the battery, which will now keep the charge constant. Now, what do you think would happen if we change the separation distance of those plates? I'm going to drag the plates apart and make D bigger. Thinking back on our unit on electrostatics, you might remember that the strength of that electric field is going to remain constant. It's independent of the distance. That means I've just increased the voltage across those plates. The charge stayed the same, but the voltage increased. That means the capacitance just went down. So the capacitance is proportional to the area of the plates and inversely proportional to the separation distance of the plates. So if you want a large capacitance, you need to have a lot of area, and those two plates need to be very close together. Now, there's another thing that we can do to increase the capacitance. Imagine we put a polar molecule in between these plates. It will rotate into this position. And what if we filled the space with more molecules? They're going to align so that the negative side will be close to the positive plate, and the positive side of the molecule will be close to the negative plate. What do you think this negative is going to do to this positive? It's going to tend to neutralize it. That will allow more charges to flow on to those plates. You'll be increasing Q using the same voltage of the battery. If C0 represents the capacitance without the material between the plates, we can multiply that value by a constant that represents how well this material increases the capacitance, and calculate the new capacitance. This material is known as a dielectric material, and kappa is a dielectric constant. If we apply too much voltage from a bigger battery to this system, what can eventually happen is the electric charges here will actually separate, and it will bridge the gap, come across to this plate, and then you'll get a cascading effect, and electrons will just jump right across. You'll get a spark. You'll burn out your capacitor. So that's one of the problems we have with these capacitors that you'll be using in lab. Don't overload them. They tell you how much voltage they can handle. And don't reverse the polarity because this dielectric material is meant to go one way. Let's talk about adding capacitors. We'll have a battery with a certain voltage and two capacitors, C1 and C2. The charges are going to flow out of the battery and flow onto the capacitors. As they do, the capacitors will start to fill up. Even if these capacitors are different sizes, when will the charge stop flowing? When the drop in voltage on the capacitors is equal to the gain in voltage of the battery. Now notice these capacitors are in parallel. So the drop in voltage across this capacitor will have to be the same as the drop in voltage across that capacitor. Now, if you're not sure about that, just think about the voltage level at this point in the circuit. Whatever that voltage level is, it's going to be the same here because it's just a wire. It's going to be the same here. It's going to be the same here because it's just a wire. We don't lose voltage across the wire. Well, that means this voltage is going to be the same here and the same here. It's all the same connected to that side of the battery. And the same is going to be said on the other side. If we said that this voltage was 0, then that voltage is 0 and that voltage is 0. And hey, all these voltages are 0. That means the drop in voltage across these capacitors has to be the same. And that's what we learned about when we studied resistors. When something is in parallel, the voltage drop across those parallel elements is the same. So we can say that C1 is equal to Q1 over V1, where Q1 is the charge that flowed onto that capacitor. C2 is going to be equal to Q2 over V2, where Q2 is the charge that flowed onto that capacitor. If I wanted to replace these capacitors with one single equivalent capacitor, it would be equal to the total charge over the voltage. And the total charge would be equal to Q1 plus Q2. Well, we can rearrange these formulas to solve for Q1 and Q2. We now replace Q1 and Q2. And I think we can see now that those voltages, V1 and V2, that's the same as V. V1 has to be equal to V2. So when we add capacitors in parallel, it's just C1 plus C2 is the equivalent capacitance. It's essentially the same thing as just making the plates larger until they touch. Now let's talk about adding capacitors in series. What happens to the charge flowing out of the battery? It goes onto the first plate, and that repels a positive off the next plate. The positive that leaves the negative plate goes on to the next capacitor, which in turn ejects another positive off the right plate, sending that positive back to the battery. So the plates are going to fill up, and the amount of charge that goes onto this capacitor will therefore have to be equal to the amount of charge that goes on to the next capacitor. So now, instead of saying that the voltages across each capacitor are the same, we're going to say that the charges on each capacitor are the same. Q1 equals Q2. But what about the voltages? The voltage drop across capacitor 1 and then the voltage drop across capacitor 2 will have to add up to be equal to the voltage gain of the battery. And going back to C1 equals Q1 over V1, we can say that V1 is Q1 over C1. And we can do the same for V2. We can even do the same for the total voltage and say it's the total charge over the equivalent capacitance. But the total charge that flows out of the battery, if we call that Q, that's equal to Q1, which is also equal to Q2. They all cancel. So when we add capacitors in series, we say 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. So for series capacitors and parallel capacitors, we have the same relationships as we had for resistors, but It's reversed. Now let's say we have a circuit that's compound. How would you add up all these capacitors and replace them with one? First, you're going to take a look at the parallel capacitors. You can just add them up. Now these series capacitors, you'd have to use the inverse relationship. And we get an equivalent capacitance of 1.6 farads. That means all of this could be replaced with just one capacitor. Now let's say we specified a battery with 6 volts. How much charge would go on each one of these capacitors? The first thing you do is you'd look at the equivalent capacitance and say how much charge is placed on that capacitor. The equivalent capacitance would have 6 volts across it. There'd only be one capacitor instead of all of those. And so now we can calculate that Q. And we get 9.6 coulombs. Well, that's how much charge will flow onto the 2 farad capacitor. If that's how much charge flows onto this plate, that's how much charge will have to flow onto that plate. There's no other place for the charge to go. Now we can ask ourselves how much voltage drop will occur on that capacitor. We have 4.8 volts across the first capacitor. That means each of the remaining capacitors both have to have 1.2 volts. They're in parallel. So how much charge ends up on that capacitor? It'll be the capacitance times that voltage. 3 farads times 1.2 volts. And that's 3.6 coulombs. Now how much charge will go on that capacitor? Same idea. Let's check this out. What's 6 plus 3.6? The total charge coming in here is going to be 9.6 coulombs. Hey, that's how much charge came into this capacitor, and we already learned that that is how much charge has to flow out of it. So it all checks out. Using all of these numbers, let's calculate the potential energy. The formula we learned earlier was 1/2 QV. And that gives us 23.04 joules. Doing the same thing gives us 2.16 joules for this capacitor and 3.6 joules for this capacitor. So what's the total energy of all these capacitors? We get a total potential energy of 28.8 joules. How would that compare to the potential energy of the equivalent capacitor? The equivalent capacitance was 1.6 farads, and the charge was 9.6 coulombs. The voltage has to be the same as the battery, that's the 6 volts. Now, don't you like it when that happens? It's the same potential energy either way you look at it. Let's try another way of looking at the potential energy formula. If capacitance is Q over V, we could eliminate the Q with C times V and end up with 1/2 CV squared. They're the same thing. Now, one last thing. Before you go and try the more advanced problems, just remember that when you close the switch and that capacitor is empty, it's going to act just like a wire. There's nothing here preventing the charges from coming on, and the current will be the maximum the moment you close the switch. Well, after a long time later, when this capacitor gets all filled up, nothing will flow through. So it acts like a break in the wire. Now things start to get a little more challenging. Let's see if we can come up with a problem here. What's the initial current flowing through the 20 ohm resistor? What's the initial current flowing through the 10 ohm resistor? And we can ask what's the final current flowing through each of those resistors? And what's the charge stored on this capacitor after a long time? Well, this will keep you busy until next time.